Good day, everyone. Today we will talk about the chain rule for functions of more than one variable. So, in single variable calculus, the chain rule allows us to differentiate composite functions. So, for multivariable functions, the chain rule becomes more powerful and versatile, enabling us to differentiate functions where variables themselves depend on other variables. So this is essential for problems involving related rates, implicit differentiation, and functions defined parametrically in multiple dimension. So our learning outcomes for this discussion is to apply the chain rule for functions of two or more variable, to use and to differentiate composite functions with multiple intermediate variables, and to solve applied problems using the multivariable chain rule. So let's start with our lesson. Now we have here the chain rule case 1. According to the book of Stewart, suppose that z is equals to f of xy is a differentiable function of x and y, where x is equals to g of t and y is equals to h of t, where both differentiable functions of t. Then z is a differentiable function of t, and dz dt is equals to d of f, the partial derivative of d of f, and dx to the derivative of dx over dt plus the partial derivative of d of f and d of y times dy dt. So for a function z is equals to f of x, where x is equals to g of t and y is equals to h of t are both differentiable, that is what the chain rule case 1 means. Now we have the chain rule case 2. Suppose that z is equals to f of xy is a differentiable function of x and y, where x is equals to g of s and t and y is equals to h, s, and t are differentiable function of s and t. Then d of z is equals to the partial derivative of dz ds is equals to partial dz to dx times partial of dx ds plus partial of dz dy and the partial of dy dz. Same with the dt. So we have dz dt, the partial, is equals to the partial of dz dx times partial of dx dt plus partial of dz dy times the partial of dy dt. So for z, f of xy, where x is equals to g s and t and y is equals to h s and t, so that is the meaning of the case 2. Now let's have an example, but before that, it is a reminder that in multivariable calculus, the chain rule for functions of several variables involves distinct rules for different types of variables. So in a typical case, we may have independent variables like x and y, intermediate variables such as u and v, which depend on x and y, and independent variable z that is a function of u and z. So the rule states that when computing the derivative of z with respect to an independent variable, for example the partial of dz dx, we sum over all the intermediate variables. So each term in this sum is a product of two derivatives, resembling the familiar one-dimensional chain rule, which is katong basic. So, one derivative of z with respect to the intermediate variable and another derivative of that intermediate variable with respect to x. So, this means each intermediate variable creates a distinct pathway through which changes in x affect z, and all such pathways contribute additively to the total derivative. So anyways, let's move to this first example. So if z is equals to x squared y plus 3x y to the fourth, where x is equals to sine 2t and y is equals to cosine t, find dz dt. So when t is 0. So it has a condition that t is 0. So for our solution using the chain rule, we have here dc dt is equals to partial of dz dx multiplied to dx dt plus the partial of dz dy multiplied to dy dt. So we have here dz dx is equals to 2xy plus 3y to the fourth, and our dz dy is equals to x squared plus 12xy cubed, because for the dz dt it respect to x, that's why this is the result, and for the dz dy it respect to y. So we have here the dx dt, we have 2 cosine 2t substituting, so we have for dy dt we have negative sine t. So when t is equals to 0, our x becomes sine 0, which is 0, and our y becomes cosine 0, which is 1. So we have here dz dt of 0 and 1 is equals to 0 plus 3 times 1 to the fourth power by substituting is equals to 3. And for dz dy, we have 0 to 1. So we have 0 plus 0 is equals to 0. So our dx dt is for 0 is equals to 2 cosine 0. So it equals to 2. For our cosine 0 is equals to 1 multiplied to 2 equals to 2. So dy over dt for the 0, we have negative sine 0 is equivalent to 0. Thus, our dz dt is equals to 3 times 2 plus 0 times 0 is equals to 6. Now, let's have another example and the last. So, if u is equals to xy raised to y, u is equals to xe raised to y, where x is equals to alpha squared beta, y is equals to beta squared alpha, find the partial derivative of du with respect to the partial derivative of alpha. So using the chain rule, we have du d alpha, or the partial, multiplied to du dx dx d alpha plus du dy dy d alpha. For our du dx, we have e raised to y, and our du dy, we have x e raised to y. So we have now for our dx with respect to our alpha, we have 2 alpha b, while in the dy d alpha we have b squared. Thus, it is really simple. By substituting it, we have now du d alpha, which is our what is as. So we have e raised to y times 2 alpha beta plus x e raised to y times b squared is equals to e raised to b squared alpha, or beta squared alpha, times 2 alpha beta plus alpha squared beta cube. So that is the answer. That's all. Thank you. God bless us all.